All right, welcome. My name is David Saylor, and I'm the director of the Urban Climate Research Center, which is housed in the School of Geographical Sciences and Urban Planning here at Arizona State University. So tonight, we're very happy to welcome you to our third annual Anthony J. Brazel Lecture on Urban Climate. But before introducing Professor Shepard, I'd like to first acknowledge that Arizona State University's 4 campuses are located in the Salt River Valley on ancestral territories of indigenous peoples, including the Acamel O'odham and Peeposh Indian communities, whose care and keeping of these lands allows us to be here today. I'd also like to give our interim director of the School of Geographical Sciences and Urban Planning an opportunity to welcome you to this event, Dean Wentz.
Thank you, everybody, for coming to this event, and for to Dave Saylor for pulling all this together. It's great to have everybody here, and really fantastic to have Marshall Shepard as our speaker. I'm not going to really say much other than it's just really great to sort of see the culmination of a lot of effort from a lot of people over the years to make this happen. So thanks for allowing me to say a few words, and welcome. And I'll pass it back to Dave for next steps.
All right, thank you, Dean Wentz. And so finally, before introducing our speaker tonight, I would like to share with you a short 2-minute video that we put together that describes our Urban Climate Research Center and some of the activities that we do here at ASU. The Urban Climate Research Center, housed in the School of Geographical Sciences and Urban Planning at Arizona State University, is home to a highly interdisciplinary team of more than 36 faculty affiliates and their students across 7 schools. The UCRC was formed in 2017 to take advantage of the amazing talent that already existed at ASU in this area, and to leverage that talent to establish ASU as an international leader in the field of urban climate. Researchers in our center work in all areas of urban climate, including air quality, hydrometeorology, and extreme heat and its impact on society. They work closely with industry and stakeholder groups, including local and regional governments, to co-develop knowledge and solutions to urban climate challenges. Each year, we engage faculty in large interdisciplinary projects and proposal development efforts. We also host 2 major annual events. Each fall, we hold a large poster event where our students and postdocs get to share their research accomplishments with colleagues and with the larger community. And each spring, we have the prestigious Anthony J. Brazel Lecture in Urban Climate, where we invite an internationally recognized scholar to deliver a public lecture on an urban climate topic of great interest to both our researchers and stakeholder networks. Thanks to the talent and hard work of our faculty and students, the Urban Climate Research Center at ASU is gaining visibility as one of the leading groups of researchers anywhere in the world working in the field of urban climate. All right, so just a little bit of housekeeping before we begin. So at the end of tonight's lecture, we're going to have about 30 minutes of a moderated Q&A. So please enter your questions using the Q&A feature in this webinar during the presentation. And so now I'd like to go ahead and introduce tonight's speaker. He's one of my favorite colleagues and collaborators, someone with who I've actually known for over 16 years now, since his days back at NASA. So Dr. Marshall Shepard is director of the University of Georgia's Atmospheric Sciences program. He received his BS, MS, and PhD in physical meteorology from the Florida State University, where he was the first African American to receive a PhD from the school's Department of Meteorology. He is a leading international expert in weather and climate and a past president of the American Meteorological Society. He also is host of the Weather Channel's award-winning show Weather Geeks, and he's also a frequent contributor to Forbes magazine. He routinely appears on television programs, including The Today Show, Face the Nation, and several others. He's won many prestigious awards for his research and public engagement. including the Presidential Early Career Award for Scientists and Engineers, the AGU Climate Communication Prize, the American Meteorological Society's Brooks and Helmut Landsberg Awards, and the Association for American Geographers Media Achievement Award. And just last month, Dr. Shepard was elected to the 2021 class of the National Academy of Engineering, which is one of the highest, if not the highest, professional distinctions granted to an engineer or scientist. So please help me in giving Dr. Shepard a warm virtual welcome. Dr. Shepard, the floor is yours. Go ahead and share your screen.
Thank you so much. And I'll go ahead and share my screen before we get started. And let's hope this cooperates. It is cooperating, but I don't know if we are. Can everyone see that?
Looks good.
Okay, great. So first of all, I'd like to thank my colleague David Saylor for the invitation to speak at the Brazel lecture. It's really quite an honor because I know Tony and interacted with him quite a bit early in my career. And so as I was thinking about this talk today, just such a gracious colleague, man. I wanted to sort of reflect on the last time I've actually spoken with Tony, and this was an email that he sent me back in 2018, congratulating me on receiving the Landsberg Award, which is a significant award within the field of meteorology given by the AMS. So it was really an honor to receive that award, and has been an honor to sort of share in this lecture series. I want to go back to my screen because the title of this talk, Can Cities Make It Rain? That's an interesting question, and one that when I started in this line of research, I think it was an open-ended question. I think it wasn't clear. I mean, people as far back as Horton and Landsberg himself and Stan Chagnon with the Metromix experiments, a series of experiments that happened in St. Louis in the 70s and early 80s, were wondering the same thing. Does the urban landscape cause, initiate, or impact thunderstorms and rainstorms? It was a question that I got interested in and started asking questions about. And I think now the answer to that question is yes, they do. But how do they do it? What are the implications? And what can we learn from a planning and practitioner standpoint? So that's what I really want to talk about today. This image that you see is from an airplane looking down at the city of Atlanta. And though there's no rainfall in that image, I think it's a really interesting look at how the urban corridor and central business district of the city of Atlanta is communicating with the atmosphere. You see that clearing there in downtown Atlanta and along the Peachtree Road corridor. And that's a classic example of how the urban land cover actually talks with the environment. Now, I want to invite you all, if you're listening in on this lecture, those of you that know me and perhaps follow me know that I'm very active in social media, particularly Twitter. So feel free to follow along on Twitter. There's my Twitter handle. Tweet out what you get from this lecture tonight and engagement with the broader public. So let's go. Let's embark on this discussion. So I want to start with this series of questions. What if you could plan or design cities to strategically leverage rainfall? What if a system of urban spaces amplified effects on weather? What if cities were making flooding worse? And what if a city was causing more rain delays at a Major League Baseball stadium? Let's go there. Here's an article in 2017 in Atlanta magazine. I suspect Phoenix has a magazine very similar. As many of you that follow baseball may know, the Atlanta Braves actually moved into a new stadium on the northern fringe of the downtown Atlanta area. The stadium used to be in downtown Atlanta. And one of the things that the Braves and the broadcasters and the media began to notice is that the new stadium was receiving far more rain delays and rainouts. And I remember tweeting something saying, well, I could have told them that because our research shows that they put the new stadium in a rainfall hotspot in the summertime, if you will. And so this reporter saw my tweet and picked it up and wrote this particular article. So it goes back to something that we had shown in a paper the previous year, which is in this region of Atlanta, right here where I'm pointing my cursor is where the Braves Stadium is, the new one. The older stadium was in this region here. And one of the things that our research had found is that over Atlanta and in the downwind parts of the city, and particularly in this region here, there's more rainfall in the summertime. And that will become apparent why as I move through the lecture tonight. But this is a good example of how perhaps scientific research could have informed the Atlanta Braves organization to put a lid or a roof on the stadium. We actually are one of the stadiums in the league that still is an open air stadium. And so I wanted to start with that because it gives an indication of how science can actually inform broader society. Well, let me give you another example. This is some work from my colleague Tom Mote and I. And what you see here in Georgia, we get most of our drinking water from surface water sources, whether it's a river or a reservoir. What you see are reservoirs built in the past 15 years, that's up to that point at least, and the red represent reservoirs that are planned. Now, I just showed you this diagram that suggests that over and to the east of Atlanta in the summertime, we receive more rainfall. With that in mind, perhaps it makes sense to consider locating many of our reservoirs in this region because we know something about the urban hydrometeorological or character of the city. And so I'm arguing that this research that we've conducted and many others as well, people like Matai there at Arizona State, for example, can inform water resources, public health, agriculture, planning, and even hazard management. And so this is the context that I'd like to use to move forward in the discussion tonight. So one of the things that you well know, Arizona State is one of the premier institutions in the world on urban and urban climate, geographical and planning sciences. And so I'm somewhat preaching to the choir here, but we know that over half of the world's population now lives in urban spaces. And that continues to be the case internationally as well as in the United States. Here's a look at population change from 2000 to 2010 based on US Census data. And you can clearly see that where you live and where I live have seen positive changes in urban spaces in the Sun Belt, in the South, Southeast, Southwest. So this is not a surprise if you've been to Atlanta anytime soon, or if you've been to Phoenix, Arizona, you know this. In fact, here's a look at, and we'll see if we can get it to go, a changing Phoenix, Arizona, as represented by NASA. I spent 12 years of my career as a scientist at NASA Goddard Space Flight Center, and I also chaired recently NASA's Earth Science Advisory Committee. So I still like to incorporate some of NASA's really cool data and visualizations and talks that I give. So you all live in this region, you're very familiar with this growth. We can mimic that same type of growth here in the Atlanta area. So this is just an indication of the growth and urbanization of places like Phoenix and Atlanta. So what I'm going to talk about today are what are the urban effects on hydrometeorological weather through the lens of both observations and modeling. And I'm also going to give an assessment of the broader impacts to society, risk, and vulnerability, because I certainly hope that in this very well-attended audience today, we don't just have academics, we don't just have students, we have stakeholders and practitioners. And so it's really the type of talk that I like to give. I want to use the framework of risk to frame some of my discussion. Now, you'll see many different sort of presentations on what risk means. In this particular characterization, risk is a function of hazard, exposure, vulnerability, and resilience, where hazards are the actual extreme weather events themselves, perhaps a heat wave or a hurricane or a flood. The exposure is the actual experience people feel or infrastructure with those hazards. Vulnerability of people and places in the urban setting is a result of increased sensitivity or differentiated exposure to those hazards. And then resilience is the ability to bounce back, the adaptive capacity that a society or people have to those hazards and risk. So let's get into the science. City landscapes communicate with the atmosphere, and I showed you that in my first graphic when I showed you the city of Atlanta and that clearing in that low-level cloud deck. This is a classic figure from Tim Oak and colleagues, sort of showing some of the science. And again, I don't want to get into the details here because it's not an urban climate class, but the bottom line is you often hear discussions about the urban heat island. Well, there's really more than the urban heat island. There's a surface urban heat island. There's a heat island that affects the atmosphere, the air temperature. There's even an urban boundary layer heat island, that first 1 kilometer of the atmosphere that still can feel the influences of the surface. And all of those things can conspire to cause changes in the atmosphere, in our weather, in storms. And so that is going to form the basis of much of what I'm going to talk about tonight. So let's talk about risk from urban storms. And by the way, that particular storm was not caused by that city. I just think it's a really cool picture. And so I always try to include it in this talk because it's just if you're a weather geek like I am, and I'm a self-professed weather geek, I don't just host a Weather Channel show and podcasts with that name. I've loved weather since I was in 6th grade. This is an amazing cumulonimbus or thunderstorm cloud. Let's take a look at this radar image that I saved from my phone one day in the summertime here in Atlanta. Notice that thunderstorm that pops up over the city of Atlanta. How would you have explained those thunderstorms? Well, I can tell you from a meteorological perspective, there was no front, there was no forcing that would have caused that thunderstorm other than the city of Atlanta. That's right. The city of Atlanta caused that thunderstorm that you see in this Doppler radar image. Well, they don't just initiate storms. This is a radar image that was sent to me excitedly by Kenny Blumenfeld in Minnesota. He knew that I did this type of research and he was tracking radar one day. And he said, Dr. Shepard, there's this line of thunderstorms, but there seemed to be enhancement as they passed over Minneapolis. And so this Minneapolis effect is really apparent. We had this line of storms, and there you see the enhancement, boom, of those thunderstorms over the city. So this falls in line with a sort of narrative that has emerged in the urban climate literature for many years. This is a paper that Karen Cito and I published, I guess, around 2009, 2010, sort of providing an overview of the various pathways that urbanization can impact the climate system. And much of the research and what we know about urban climate falls in this regime here. There's been a lot of work done on the urban heat island, and certainly a lot of that work was done by Tony Brazel and colleagues at Arizona State University. Much of my focus has been spent in these two areas, clouds and precipitation and land surface hydrology. I've been asking and answering fundamental questions about how the urban environment affects the hydrometeorological character around cities. And so this is a really old paper, it's about 10, 12 years old now, but I think it's aged well because many of the same things that we discuss are very relevant and salient today. So let me just walk through a few pieces of evidence. And yes, some of my focus will be on Georgia, but to be clear, this urban rainfall effect that I talk about has been observed all around the globe. So this is some work from my colleague Tom Mode and one of his students and I. And what you see is a climatology of rainfall from radar. And the green colors represent heavier rain or more rain. And you see some things that you would expect in Georgia. For example, this is mountainous. We get quite a bit of rainfall up in the mountainous terrain. Down here in the coastal plain, as we get close to the coast in Florida, we also have a great deal of thunderstorm activity. But let's focus on Atlanta. Look at this area here in these yellow boxes. Over and downwind, again, our climatological downwind region is the eastern suburbs of Atlanta. Our prevailing wind flow is generally westerly to northwesterly. So look at this region. See these anomalies that pop up over and downwind? There is nothing fundamentally different climatologically about this box here, but notice there's no anomaly. This was a clue that something was going on, and we've seen similar things. Stan Chagnon and colleagues saw similar things after the Project Metromex experiment. There's an urban effect on rainfall. But alas, it's not just rainfall. Look at this data from Tony Stalin showing lightning. He combined lightning data for 8 years under westerly wind flow. And what he found was something very similar to what I have found with the rainfall data. That is, over the city and just to the east, there's more lightning in the warm season. So if you want to, and this is not a sort of a flippant statement, if you want to lower your chances of being struck by lightning, you might buy a house here, here, or here on the southern or western side of Atlanta, because this urban effect on lightning is very real, and we've seen it many times in studies. Well, even though we have a downwind regime for rainfall and urban effects, that can shift depending on the prevailing wind flow. So here's a case where we have thunderstorms that are actually moving from the northeast toward the southwest into Atlanta. So I'm going to do a little meteorology 101 here. So here's a thunderstorm, and look at that little arc region. See that curved feature? That's what we call in meteorology an outflow boundary. So if you're out playing softball or doing something out in the yard and you feel a cool breeze before it starts to rain, you're probably experiencing that outflow boundary as it moves by. But notice what happens as that outflow boundary moves into the downtown Atlanta area. Watch what happens right about here. Boom! A new thunderstorm is initiated along that outflow boundary. Now, that outflow boundary is likely itself lifting the air, but we think the city of Atlanta was giving it a boost as well. And I'll talk about the physical mechanisms behind why it happens later in the talk. But this is just more examples of the urban rainfall effect. Now, Matt Georgescu, who I was talking with earlier, and who has actually published a really innovative paper himself just recently on the urban rain effect from a broader climate change context, is a person that uses models. I use models as well. In weather and climate, we actually have these models that can actually simulate the atmosphere. It's in fact how weather forecasts are made. I get this question all of the time. Well, how do you know what the weather is going to be 2 days from now, or 5 days from now, or 7 days from now? We use models. We have these complex models in which we solve very complex equations coupled or connected to land surface models. And so using these, we can make weather predictions, but we can also do research and development. And so here's a really old study, a paper we published back in 2005. And what you see here, I'm going to kind of set the context. Down here, you see weather radar for Houston, Texas on a given day. Here's Galveston Bay, city of Houston is right here. So we see something that we'd expect on a summer day in Houston. You see thunderstorms developing along the sea breeze front, all along the coast around Galveston Bay, but focus on these thunderstorms here. Now we ran a weather model. These two on this side, we took the city of Houston out of the model. In these runs on the right, we left the city of Houston in the model. Now, these purple surfaces are clouds, cloud water. You might see these little yellow iso surfaces, that's rainwater. And the black lines represents the low level or surface wind flow. Now, I'm a professor, so I've got to give a little pop quiz here. What do you notice differently about the simulation of this case over here and over here? Well, that circle gives it away. Notice only when the city of Houston is included that we get this extra thunderstorm activity that was resolved over the city. So this is a case where the sea breeze front is interacting with the city of Houston to produce more enhanced thunderstorms over the city. Now, we took that a step further. We actually worked with some planners, urban planners, and I know colleagues there at Arizona State have very good relationships with the urban planning community there in Phoenix and surrounding areas. We worked with some urban planners in Houston for the Houston Galveston Area Council. They found our work very interesting and said, hey, we'd like to work with you on this. So what they did is they used some agent-based modeling, a modeling system called UrbanSim. and they projected what Houston's urban land cover was going to look like in the year 2025. That's about 4 years from now. But remember, we did this study back in 2010. And what we found is we took that same exact case that I was showing you here. We initialized the model with the same weather. The only thing that was different is we put a 2025 Houston land cover in the model. And we found that we could change the climate in terms of rainfall simply by changing the urban land cover. Nothing else changed. And so this gives us an indication that urban landscapes can influence the hydroclimate around cities, perhaps at the scale of some of the greenhouse gas induced changes that we're seeing in the climate as well. And that's why Matt's paper was so important, because he's sort of merging some of the thought on both of those processes. All right, so by now, because I've given this talk a few times, people are saying, well, okay, well, how does a city initiate or affect rainfall? We think there are 4 reasons, and there's still a real research question in sort of partitioning out which is the dominant, which happens at certain times, which happens at other times. One, that well-studied urban heat island. Cities have urban heat islands, and due to these urban heat islands, the air is more likely to want to rise. There's atmospheric destabilization through thermal mixing because of that low-level heat source, if you look at this little diagram here. So this sort of urban environment is a localized heat source, so it can actually induce circulation. So I want to kind of go to this, look at this right here. You might get rising motion over the city. If you go to the beach, this is exactly what happens when you have a sea breeze front. The land heats more rapidly than the ocean, and so you get a low pressure developing over the city, you get rising motion, and you get a circulation, and so you get these sort of urban induced convergent zones and so forth. This is some recent work by Sano et al. 2018. Secondly, cities have buildings, and when wind blows through a series of buildings, there's mechanical turbulence that's generated, and that mechanical turbulence and aerodynamic roughness can cause convergence. And when the air converges, it rises. And so any basic meteorology class, and I know that there's a rumor that there are some students from a 2000 level Arizona State weather and climate class that may be listening in. And so those students may have learned by now that in order to get clouds and thunderstorm development, you need a source of lift, you need moisture, and you need an unstable atmosphere. And so cities provide a destabilized atmosphere. It can provide lift through convergence. Another thing that clouds need on planet Earth are condensation nuclei. These seeds need something to form on. Cities are areas of pollution and higher air quality or lower air quality, depending on how you frame it. And so cities may serve as sources of these condensation nuclei or seeds that we need for clouds. And then finally, my good friend Bob Bornstein and colleagues have argued that sometimes storms, as they're approaching cities, and perhaps some of you've experienced this or seen this anecdotally, as storms approach a city, they split or bifurcate and go around the city. And there's actually peer-reviewed research that suggests that that's the case. Now, I want to deal with this aerosol effect because people sometimes just don't believe me when I say that, seeding the atmosphere can produce clouds. So I want to ask a question here for those of you that eat meat. How do you prefer your snow, beef or pork flavored? That's somewhat of a joke, but the reality is this is a case that I published with a colleague back in 2011. Look at this radar image here. And again, this was off my phone. I took a picture of it, so that's why it's a little bit rough. This is a plume of snowfall. See that little narrow plume just downwind of Dodge City, Kansas. Now here's the satellite image showing the snowfall on the ground the next day. And you can indeed see that snow only fell in that very narrow plume. Now, the National Weather Service Dodge City started looking at this, and we started looking at it as well. And lo and behold, what we think was going on in this very localized snowfall case is that you had a power plant down here to the southeast of the city that was providing moisture and some aerosols. You had some slaughterhouses here that maybe had some emissions as well. And those two sort of industrial sources were seeding that little snow plume. So there's a very clear example of how aerosol processes, at least particulate matter in the atmosphere along with moisture, can cause snow. I saw this very recently. This is a radar image from just a few weeks ago in Alabama, and notice these plumes of clouds and rainfall sort of moving off in this direction to the southeast. This is a narrow band of industrial enhanced snow over Pickens County in Alabama. The steam was being produced by a Weyerhaeuser paper plant. And so the added moisture and aerosols and warmth are essentially seeding those clouds to produce rainfall and snow, and in this case, snowfall. So clearly we know that aerosol processes can affect clouds. Now, the other thing that we know, and I mentioned this, is that storms can split or bifurcate. Here's a case that Bob Bornstein has shown of a larger storm approaching the city of New York and then splitting and bifurcating around the city. I actually have a hypothesis of what's going on, although I haven't tested it. So I hope people like Matt are listening in on this, because I saw a little evidence of it in a study that we did. I think that cities are actually behaving like von Karman eddies or mountains in a flow over the ocean. Here's a satellite image. There's a mountain there out on an island. The flow is coming from the northwest. When that flow impinges upon or hits that mountainous terrain, it forms von Karman eddies downstream. I think cities do that. I don't know if it's a physical effect or a thermodynamic effect with a thermal bubble. It needs to be investigated, but I really believe that there may be some von Karman type flow downwind of cities. Now, I want to shift gears because I've talked to you about how cities affect rain that falls from the sky. Let's talk about other risks associated with urban precipitation. And here you see flooding in Ellicott City, Maryland. Urban flooding is a significant problem. I don't know how much of it you deal with in places like Phoenix, but I know that the monsoon season is a primary rain producer for you. So I can imagine that you deal with urban flooding in that region as well. And so I want to talk about, again, the risk. Remember, I'm framing everything in terms of risk of urban floods. Now, quiet as kept, fourth grade lied to you. And what do you mean by that, Dr. Shepard? When we were in fourth grade, we probably learned about the water cycle. We learned about evaporation, condensation, precipitation, runoff, infiltration, and so forth. And that is indeed the water cycle. But what we didn't learn in fourth grade is that the water cycle is different in a natural environment as compared to an urban environment. In fact, you can see here that in an urban environment, there's far less infiltration because of all of the impervious surfaces. In an urban environment, there's significantly more runoff, which can exacerbate flooding. And perhaps due to the research that we've done, the precipitation is different in the urban environment as well. So cities modify the water cycle. So this is some work by Neil Debbage and myself from 2018. We looked at watersheds around Charlotte, North Carolina, Atlanta, Georgia, Greenville, South Carolina. And essentially the bottom line is we found that more urbanized watersheds exhibited a greater number of high and low threshold exceedance, as well as larger peak unit discharge values. Now, this has direct implications for practitioners in the planning, transportation, perhaps even emergency management space. And it's not rocket science. We know that if rain is falling with greater intensity, perhaps in addition to because of climate change, and it's falling onto impervious surfaces, it's running off with greater runoff rates into our streams, lakes, and so forth, which become full, and it leads to flooding. So one of the key considerations from that study is that it's important to consider the extent, configuration, and positioning of urban development when devising land use policies aimed at minimizing stream flow due to urbanization. So here is a practical result of urban hydrological research that is of value to city planners. is of value to practitioners, transportation planners, and so forth. And in fact, urban design guidelines, this work building on Oak 2017, Kryenhoff 2014 and 2020, Lenzholer 2015. This is a slide that I received from Jamie Voigt. Continued development of urban canopy layer models, which is these sort of very high level focus models embedded in some of those regional models that I talked about earlier, to better represent these hydrometeorological processes, can be used to assess urban design guidelines and contribute to urban adaptation. So a key point of these last two slides, and even some of the things you see in terms of different greening scenarios, is we believe that we're at a point where these urban design guidelines can be informed by this urban hydrological and urban hydrometeorological modeling that we now do. The problem is, and something that I've found, and I know many of my colleagues at Arizona State have found, but you all are better at it than some, is that the urban climate community doesn't necessarily talk to the planning community and vice versa. So how do we really effectively transition these things across that gap? I think those are really open-ended questions, and I know folks there at Arizona State are thinking about them. Now, I also wanted to mention that urbanization has an effect on winter precipitation too, and you all certainly don't get that much winter precipitation. We don't get that much in Atlanta either. But look at this image here showing the relatively lower snow cover because of the urban heat island. The city's warmer, and so snow that falls there is more likely to possibly melt because of the urban heat island. Urban wintertime precipitation is less studied. There are some studies. One of my students, Brad Johnson, and I published a paper in Urban Climate looking at regions along the urban I-95 corridor from Washington, D.C. up to New York. And we found that as the distance to the urban center increases, there's more mixed precipitation. Well, what do you mean by that? Basically, in a nutshell, what we found is that because of these big cities, D.C., Philadelphia, and so forth, oftentimes in those areas, the temperature is hovering just around the freezing mark of 32 degrees, but in the cities, they're usually above 32. So things that fall are typically going to melt. You're not going to get as much freezing rain or perhaps even sleet. As you move away from those urban centers, you start to get into the mixed precipitation, freezing rain, sleet, and snow. So this is some of the work that we've done to dabble in urban winter precipitation. So I want to get ready to sort of come to a close here. I want to point out this document. It's actually a bit old now, but I think there's still some really useful information in it. I served on a committee that the National Academies pulled together several years ago. I suspect Dave Saylor may have been involved in this as well. And we thought about ways of making applied climate science actionable, particularly from an urban hydrometeorological perspective. And so here is a look at some of the things that we talk about in this document. It's a free download on the National Academy. We talked about end user needs of urban meteorological information, end user needs not being met, underutilized urban forecasting monitoring capabilities, communication, and so forth. And then we also provided a synopsis of emerging technologies and the science, what we know about urban meteorology. And then this final chapter sort of looked at short-term challenges and future needs in urban spaces all throughout the United States. So I think, I want to end on this slide. I think this middle bullet talks about, or this middle oval talks about enhancing the capabilities of the city for the provision of weather, water, climate, and air quality information. And the boxes feeding into this really talk about, from a World Meteorological Organization perspective, what needs to happen in order to enable short to long-term decision-making for cities. And so this is where I think we need to go. I mean, one of the areas that I'm working with right now, I received funding from NASA through a large interdisciplinary program to move this research in urban hydrometeorology from is it happening and why to how can we better predict it so that decisions can be made. So hopefully this kind of answered the original question that I posed. Can cities make it rain? The answer to that is clearly yes. I mean, I think we've sort of answered that question definitively in the last decade or so. But I think the next question is, okay, what do we do with that information? I'll stop there, and I look forward to entertaining some of your questions. Thank you.
All right. Well, thank you very much, Marshall. That was an amazing talk. I think you really sort of hit that sweet spot of mixing good science with a little bit of planning and policy sort of overtones. I really liked the bit about actionable urban hydrometeorology. And yes, I was at that National Academy meeting with you. That was quite a long time ago. But,
Yep.
So we're at the Q&A part where we're going to have a moderated Q&A by my good colleague, Dave Hondula, who's an associate professor in the School of Geographical Sciences and Urban Planning here at ASU. And he has been gathering together all your great questions and might have a few of his own. So I'll go ahead and let Dave Hondula take it away.
Thank you, Dave, and thank you, Marshall. Hopefully you can hear me all right.
Fantastic.
I can. Yeah, and thanks for the terrific talk. Wonderful to hear your remarks. We have a mix of questions across the board, some related to atmospheric science, some not related to atmospheric science, and hopefully you'll be welcoming of that mixture. Well, let's start with
I can take any question, happy to.
Let's start with some of the questions that are in the atmospheric science domain. And one of them comes from Randy Cerveny, professor in our unit, whose work I imagine you're familiar with. He noted that he and our colleague Bob Balling had a study a number of years ago looking at urban precipitation enhancements that found an interesting weekend effect where there's more rain on Saturdays and Sundays than Mondays and Tuesdays, perhaps due to higher pollution occurring at the end of the week. So I'm just curious if you've, or they are curious if you've had any similar observations about weekly patterns, perhaps other interesting temporal patterns in this urban precipitation effect.
Yeah, thank you for that question, Randy. And I was certainly aware of, I think we've cited some of your work in the past. You know, interestingly enough, when I was at NASA Goddard Space Flight Center, there was a guy named Tom Bell, and I don't know if, Randy, you are familiar with his studies, but he also found this interesting weekend effect. And I think there's some credibility to it because we clearly know that there is a diurnal and a weekly cycle in aerosols. And I think one of the sort of unanswered questions in this urban rainfall mystery is the sort of co-effect of aerosols in urban landscapes. Many of the studies that you see typically look at urban land cover and taking cities out and varying the urban morphological parameters and buildings and so forth. Only now are we starting with the Whorf-Kim model and other capabilities. Only now are we starting to be able to sort of integrate correctly, at least, the urban aerosol effect as well. There's a paper that Steve Burrian and I published in Houston a couple of years ago. I'm sorry, more than a couple of years ago. I think it was around 2005 or so. And we also hinted at a possible weekly cycle or a weekend rainfall max as well. We didn't feel confident enough in that study design saying it with conclusiveness because that really was not the objective of that study, but we saw hints of it in what we've done. So I definitely think that you and Bob were sort of on to something that Tom Bell certainly showed using some satellite data sets. But I think that it's a rich area for further study, just the sort of temporal cycles and spatial patterns of aerosols and this urban rain effect.
Thanks, Marshall. Our next question comes from a colleague who you may encounter in the halls of the National Academies. Congratulations again on your recent appointment. This comes from Billy Turner, who remarked that he really enjoyed the presentation, and he comments that you made a compelling case for the city as a unit. To what extent can we think about the configuration and composition of cities as important variables that could shape the patterns that you talked about?
Excellent question. You know, there are so many tentacles to that question that it certainly would be a 5-year proposal in itself. You know, questions arise, for example, do low profile cities that don't have high or large buildings, is their impact less on this urban effect because there's less of a convergence or a mechanical turbulence profile? I think there are legitimate questions about the contiguity of the sort of the arrangement of the urban spaces and sort of their ability to collectively create this thermal signature or thermal anomaly that would induce an urban circulation. There are questions about the size of the city. What size of the city can actually, we know any size city can produce a heat island, but is there some sweet spot size that will induce this enough of a circulation to generate the urban rainfall effect? And Devna Yogi, who's now moved to the University of Texas from Purdue, has done work along with Paul Schmid in that regard. So we think we do have some idea about the size. It's typically a moderate sized city. By the way, I think I cut off my slide presentation too soon, but I actually did have one extra slide in there that we actually published a study looking at Phoenix, Arizona, and the urban rainfall effect back in the Journal of Arid Environments back in 2006. And what we found is that there is this urban anomaly up in the low, I guess is the lower Verde, the valley out to the, I guess, east of the city. And what we found, or what we hypothesized, is you get the storms that are forming out there in the mountainous terrain, but they're putting out outflow boundaries. And those outflow boundaries are then propagating back towards Phoenix, and they're interacting with the fringe of the urban sort of non-urban boundary, and you have a convergence zone that sets up there in the lower Verde region, and we found an anomaly. So I just wanted to sort of share in the wealth there that there have been studies, not just mine, that have shown that arid cities, even though you don't get as much rainfall, can still have an urban effect.
Thanks, Marshall. Our next question brings together two worlds that you talked about, the world of urban heat research and the world of urban precipitation research. And some of our colleagues here at ASU have been deeply invested in measuring shade in the urban environment and understanding how that impacts the thermal experience. Our next question speaks to the intersection of that issue and urban precipitation. Is there any chance that as these cities are generating additional precipitation mechanisms and clouds, that those clouds are casting more shadows on urban residents and perhaps are indirectly making conditions in the city more comfortable for people?
You know, that's a really interesting question, and one I haven't actually thought about, but there's certainly several papers in the literature that have shown sort of the urban effect on cloud distributions. And sometimes those clouds never precipitate. So I think it's a reasonable assumption to suggest that there may be, and one of the things I want to kind of emphasize, it may not have come through as clearly. Much of the work on urban effects on rainfall have been focused on the warm season, because that's when you're more likely to sort of have these sort of forcings that are not dominated by large scale weather patterns. But we've also seen in recent studies that urban environments can affect sort of these large scale weather systems too. So I though I've not seen any specific sort of link between sort of shading and urban clouds, I think that that's a reasonable assumption if you look at the literature. I will also say, Ming-Lin Jen and I published a paper several years ago that talks about how, and again, this is relevant to those of you doing urban heat island research, we showed that urban air quality and sort of aerosols can actually reduce the magnitude of the urban heat island. So if you have a dirty atmosphere or sort of aerosols that are either, if they're sulfate based, more scattering, or if they're perhaps even more black carbon based, they may be more absorbing. But that paper looked at whether these aerosols can actually reduce the magnitude of the heat island. Now, in that sense, that's a good thing. And the reduction of the heat island can in turn sort of reduce some of these circulations that we've talked about as well.
The feedback mechanisms, the potential feedback mechanisms in both directions are so interesting. You mentioned that most of the work is focused on the warm season. We did have a question about potential links between urbanization and the winter storms in Texas earlier this year. Your answer makes me think that it might be a little premature to have any ideas about linkages there.
Yeah, I honestly haven't really given that one much thought, to be honest with you. I mean, I'd be kind of curious sort of where, and maybe I didn't see it in there, but where the question's kind of sort of going. I think I need more context. By the way, I just put in the chat box a link to that study we did that was that I mentioned about the urban effect around Phoenix, because I did see a couple of questions in the Q&A about whether this is possible in arid regimes. So.
All right. Well, let's shift the discussion for a little bit. You did such a good job keeping your talk on time that we have ample time for a discussion. So we hope you'll entertain a few questions outside of
sure.
atmospheric science, and then we'll return to
I'll
some others.
answer any questions anyone has. And if I can't answer it, I'll say so.
We have to perhaps lighten the discussion for a moment. We actually have two questions from Matt Georgescu, who you mentioned by name multiple times. And he's very appreciative and says it was a fantastic talk.
Yeah, he's just got to stop trying to steal my graduate students. I'm just kidding. No, we joked because the outstanding Neil Debbage, who I mentioned, I know that there was a slight chance that he was going to come out there and work for Matt, so that would have been a good choice either way.
Still a sore subject around here. So Matt has two questions. I'm going to save the more substantive one. Well, actually, there'd be some debate about which one is more substantive. But his first question is, how is Georgia football looking for the upcoming season? We know you're a big sports fan.
Oh, big sports fan. And you can see I'm wearing my Georgia, because I am actually the Georgia Athletic Association Distinguished Professor of Geography and Atmospheric Sciences. We have a pretty successful athletics program. So they actually have a couple of endowed professorships on campus, like the IBM Professor of Computer Science or the Coca-Cola Professor of Business. I'm the Georgia Athletic Association Professor of Atmospheric Sciences and Geography. And so, of course, you never bite the hand that feeds you. No, I'm kidding. But I think we're going to have a really solid season. I mean, I'm not being a homer on this. And by the way, Matt, I'm actually a bigger Florida State football fan than a bigger Georgia Bulldogs. I actually have all 3 degrees from FSU. So if Georgia was playing Florida State, I would actually pull for FSU. But luckily, that doesn't happen very often. So I think we're looking pretty good.
Fantastic. Okay, for a question that I'm sure you were anticipating, you're, of course, widely celebrated as an expert communicator, whether it's true through your professional positions with the Weather Channel or awards you've run. So we need to hear some advice about being a great science communicator from you. And maybe the first, we have a lot of related questions, and as I sift through them, maybe the first question that you could answer is, what specific training would you recommend, or maybe that you've received, that's helped you become a better communicator? Is this feedback and trial and error through the years of conference presentations and stumbling over your own remarks? Have you attended particular classes or programs? Do you have a coach? What would you advise, particularly for the many students who are on the line who are aspiring to be great science communicators like you?
Well, the first thing and I'm going to come down the road of all academics on this call and on this Zoom, I think we need to fundamentally change the paradigm of how we're training graduate students. What I mean by that is, and all of our programs are guilty of it, we do a good job at training graduate students to be sort of go to class, write their theses, write a dissertation, go to a conference, present it, and do the same thing. I call it the academic treadmill. But we rarely train what I call students to be end-to-end scientists. And so that's something that I've been talking quite a bit about. I believe we need to train within our undergraduate and graduate programs students to be end-to-end scientists. We need to train them to not just know their discipline from a technical standpoint, but how to engage in public policy spaces, how to engage in social media, how to engage in communicating to the media and so forth. One of the things that people often say to me is, wow, I'm really impressed that you can do all that you do and you still tweet and do that new stuff called Twitter. Twitter's not new, by the way. It's been around for a while. And they sort of say, yeah, they sort of speak of all of those activities as if they're add-ons. I don't fundamentally see it that way. I see what I do as fundamentally who I am as an academic, as a scholar, engagement. And so, by the way, I still generally lead my department in publications and peer-reviewed journals and grant dollars each year as well. So, I frown upon this notion that you can't sort of have an integrated approach to scholarship that's beyond the ivory tower. So to kind of answer your original question, Dave, I wrote an article and I was trying to pull it up there, but it looks like it's the Forbes paywall is behaving tonight. I wrote an article called 9 Tips for Communicating Science to Non-Scientists. And so I would invite everyone that's interested in this topic to read that, because the reality is we aren't trained I mean, some of this is just my personality and my sort of, some of it is personality driven. I've had people say, well, I don't have your personality. I'm not comfortable getting in front of the Weather Channel cameras or testifying before Congress. I said, well, if you can't do that, I bet you can write a blog, engage. I think it's so important that we as scholars engage, because if we're not there in those public spaces, people with agendas and false narratives will happily fill the voids that we leave behind. I also think academic environments have to incentivize young scholars to engage, because you see young tenured professors and young graduate students that focus on publishing or perishing or getting grants, because those are the metrics that are valued in academic spaces. But guess who is often doing the most innovative research? The research that is most likely to capture the attention of the media or of a congressperson is oftentimes our bright young scholars, young professors and so forth, but they're not incentivized to do those things because they're on the academic treadmill and they know the metrics that are valued by the academic sort of framework. So those are some of the challenges, but to run through some of the 9 things there quickly. Keep your messages in threes. The studies show that messages in 3 still resonate. Use the 3M approach, miniature, meaningful, and memorable when you're messaging. Use analogies and so forth. Avoid jargon as much as possible when you're talking to broader audiences as well. Know your audience. I mean, I can't give necessarily the same talk to the Rotary Club that I give to the AMS or the AGU, but I see academics do it all of the time. They go in with their same AGU talk to the Rotary Club. So it's important to know your audience. And finally, I would say connect on a value system level. Don't go into a stakeholder group or practitioner group sort of blazing with your academic credentials and graphs and charts and scholarly papers. Go in with a co-production knowledge framework, sort of working together, listening and understanding the values that connect with whoever your audience may be.
It's so interesting that you say that. There were times in your talk, and I appreciate your response there. There were so many times in your talk where you posed a question to us or challenged us to think a little bit. The Zoom webinar format is not the most engaging. You're staring at a black box or maybe a few cartoons, but I felt at times like we were in the room together, just the way you craft your talk, and appreciated that. Going back to your remarks from before, you'll be pleased to know that we do have some administrators at ASU on the line who I imagine their ears perked up a little bit hearing some of your comments about the system and incentives, and we definitely appreciate those. I also want you to know that some of the questions related to being a better communicator have come from time zones all around the world, including in Singapore. I can't imagine exactly what time it is there, but please.
Shout out to Winston Chow. I bet he's listening in.
That is a good bet. Yes, that is a very good bet. Okay, let's go back to atmospheric science one other comment just about presentations and communications. It seemed to me like you were really enjoying yourself giving the presentation. You were smiling, lighthearted, making jokes. Some of us on the line get very nervous and anxious, even if we're just in front of our computer. So what's your secret for being so comfortable in the presentation setting, or at least what appears to be comfortable?
I think some of it is just practice and doing it. I mean, I've been doing this a long time, and I would say one thing, and I would encourage some of those administrators and perhaps deans, and one of the best things that I had early in my career at NASA was media training. And at the time I didn't quite understand why we were doing it, but then I realized the longer I stayed at NASA is a very well-regarded science agency, but they also understand public engagement. In fact, they've mastered it. And so they wanted us as scientists to be comfortable in front of cameras or engaging and speaking in public and so forth. I personally also, as an undergraduate student at Florida State, took public speaking courses, and so forth. But it just goes back to this thing that I even tell students that are interested in coming into my program at the University of Georgia today. Don't just focus on your technical and science skills. Focus on your language art skills and writing and speaking and so forth, because all of those things are going to make you a better end-to-end scientist. But at the end of the day, it's like everything. The more you do something, the more you are comfortable with it. I will be candid. I was always that person in high school and in college that, I was involved in a lot of different things, president of my fraternity, senior class president at Florida State. As sort of external as though many of those things seem, some of the skill sets honed in those capacities have very much helped me in my public engagement as a scientist.
Great, thanks. And I'm sure your answers are really helpful to the many folks who are on the line. We'll wrap up with two more atmospheric science questions to bring it back to our topic, and then we'll hand it off to Dr. Saylor for any final remarks and questions he might have. We have to ask a COVID question given the times, and hopefully we're putting some of the difficult aspects of COVID behind us. But I think we're going to see scientific study of what has happened with COVID for years to come. And one question we have from the leader of our Sustainable Cities Network here at ASU, which is a practitioner-focused convening group, she notes that it's clear that there were all sorts of impacts on city dynamics and city life because of COVID. Is it possible that we'll see some evidence of those changes to our cities in precipitation and climate patterns in and around our cities? Do you think we might see research head in that direction in the years to come if we don't have it already?
Well, I think one of my colleagues and one of your colleagues, and actually a good friend of mine and colleague, Vernon Morris, who's now at Arizona State, I think Vernon's already engaged in a project, I believe, where they're sort of looking at sort of aerosol, atmospheric chemistry, clouds in the wake of the COVID shutdown. And so this reminds me of some work that Randy Travis did after 9/11. Of course, all of the airplanes are grounded, and so we had no contrails in the sky. And so that was a really interesting experiment that we were able to sort of look at the impacts of no contrails on the radiative properties in terms of climate change, because we know these high clouds have an implication for sort of the amount of energy and the radiative balance of our climate system. So I do know that there's early evidence that we had cleaner air in certain cities, that there were declines in carbon emissions and so forth. Those were only temporary blips. I think as we start to normalize, I think we'll sort of see things sort of rebound back to where they were. But I think it's important to note that that shutdown clearly illustrates that human activity can affect things like aerosol cycles and perhaps cloud cycles and so forth. Have we looked at the impact of rainfall? We haven't, but I know that there are some groups out there starting to sort of investigate, taking advantage of this unique natural experiment.
Great, thank you. And to return to Matt's multi-part question from before, this one is not about football, and I'm going to try to combine a part of another question that was asked. And thank you all, everyone who's asked questions. We've had overwhelming interest, and I'm sorry if we haven't been able to answer yours. So Matt would like to know, as you look into your crystal ball, what is the next big frontier for urban climate research? And as you think about the answer to that question, as we enter that new frontier, what can we be doing to erode or shorten this divide gap that you raised between the urban climate community and the planning and practice community? How does the new frontier look better than this gap that we have right now, whatever that new frontier is?
Yeah, I think the answer to that lies, Dave, in a project that you, myself, and Dave Saylor are currently involved in. I think both answers. So we are involved with a multi-institution effort involving Arizona State, University of Georgia, Georgia Tech, and North Carolina A&T, proposing an engineering research center that is going to fundamentally go on the offense, Matt, football, go on the offense instead of defense when it comes to urban climate. What I mean by that is we're on the defense in the sense that we're in a city, it's hot because of the urban heat island. There are vulnerabilities and risk associated with it. There's issues with hydrology that may lead to urban flooding. I've shown that there may be impacts on rainfall. So we're on the defense. With this ERC, we want to go on offense. We want to actually see if we can mitigate or control the thermal environment. And I mean, not just with albedo modification or green space. We're talking about some really innovative urban thermal control, and in some cases with the goal of minimizing or controlling urban thermal environments for thermal justice, as we're talking about. So I think one of the frontiers is really taking advantage of the emerging engineering and science knowledge we have to move beyond sort of what I call the sort of standard mitigation practices in urban environments, vegetation and albedo, to more aggressive methods of redistributing or repurposing heat in a way that's equitable, or perhaps even for use in other parts of the urban system. So I think that's the answer to Matt's first question. And I think the second question is sort of embedded in our approach there too. I know people there doing co-production of knowledge. We've got to kind of really engage with co-production of knowledge on steroids. We have to not only engage stakeholders and practitioners in projects like that from the start, but we have to really think carefully about, what the end games are in these efforts. Oftentimes we start these big projects and we go find an HBCU, or we go find a planning department that's willing to partner with us. And, it's kind of a sort of an end to end sort of here we go, pass it along. But when in this sort of co-production framework, it's kind of a hand-in-hand process at every step of the way. And so I think that we're going to increasingly see that.
Marshall, thank you so much for fielding this wide range of questions. I know I've really learned a lot from you, and I've appreciated hearing your perspectives, and I'm sure the same is for everyone else on the line. So thank you again. And with that, I will return the floor to Dr. Saylor. Thank you.
Thank you so much, Marshall. I mean, this has really been, I'd say, a master class in science communication, both before the Q&A and after. And in fact, Dave Hondula, thank you. It's been a master class in moderating Q&A. I think this was a very enlightening and exciting conversation to be sort of part of. And so we do thank you for that. I do also want to wrap up by thanking the people behind the scenes that have really made this event possible. So thanks to Megan Martin, David Brazel for their help in organizing the event, the University Technology Office team, and Peter Crank and Taylor Sapero for their work behind the scenes. And finally, for our audience, for their participation today and their attention to the Q&A, and really giving us some great questions to discuss. And I do encourage you, I'm sharing our final sort of closeout screen here. If you want to hear more about what's happening at the Urban Climate Research Center, visit our website, follow us on Twitter. We don't quite have as many followers as you do, Marshall. It would take quite a long time for us to get there. But nevertheless, we do promote our activities, including what we're doing with this Engineering Research Center proposal. So come learn more about us, and stay tuned for next year's lecture, which we've got it's a tall order to come anywhere close to what Marshall has given us tonight. But we'll do our best to repeat this performance with someone else. And so with that, I'd just like to say thank you all and have a great evening.
Thanks, everyone. Take care.
Thank you,
Thank you, Dave.